I want to talk about limits, particularly limits for functions on more than one variable. But I thought we'd start by reviewing that old idea of limit from Calc 1, right? The idea that when I say the limit as x approaches x naught of f of x equals L, I'm thinking about something that might look like this. Certainly doesn't have to, right? There are many different pictures I could draw, but the idea is that as x gets closer and closer to x naught, then the y values get closer and closer to L. When we really think about a limit, what we're saying when we write this is I can make the y values be as close to L as I want by making the x values stay close enough to x naught. Formally, we write the limit as x approaches x naught of f of x equals L if for every number epsilon bigger than 0, there exists a corresponding number delta bigger than 0 so that the absolute value of f of x minus L is less than epsilon whenever 0 is less than x minus x naught is less than delta. I want to talk about what these absolute value statements really mean. This first one is talking about keeping the y values close to L. So f of x minus L is a distance between a y value and L. In absolute value, it's a distance, and I'm trying to keep that less than epsilon. So in my diagram here, these distances here, that's my epsilon. That's the as close as I want, right? I'm supposed to keep the y values as close to L as I want. How do I do that? By controlling the distance the x's are away from x naught. The absolute value of x minus x naught less than delta is a claim that I can make the y values be as close as I want within epsilon of L by keeping the x's close enough within delta of x naught. In my diagram here, I see that, well, if I want y values in this red range, I have to keep my x's between right here and right here. And what I notice is that this length is a little longer than this one. Well, I went 1 delta, so we always took the smaller one, right? Because if I take the smaller distance on this other side, well, I'm still in the right interval and everything's fine. The last thing to consider is that I throw a 0 here. I'm making this distance be positive. Well, that's because I don't want to get to x naught. Everything in here serves a purpose, right? I want to keep my y values within epsilon of L. To do that, I have to keep my x values within delta of x naught. If there is a delta for every single epsilon, then this limit exists. Okay, so I want to talk about limits for functions on more than one variable. Right now, I want to talk about limits on functions in 2 variables. So I have to have this same idea, right? Okay, so instead now of having a limit as x approaches something, right? This part, the x approaches, and this part down here is about what's happening in the domain. Well, if I'm thinking about a function on 2 variables, then the domain's in the xy plane, right? I'm not going to have a number getting close. I'm not going to have x getting closer to a number. I want to have an ordered pair getting closer to a point in the domain. And I should be able to draw a picture that corresponds to this. Of course, I'm not actually going to try to draw a 3D picture, but here I have one. Right here I have a function. Z equals f of x, y. Right, there's my function. And I've graphed a hemisphere here, it's a GeoGebra printout. But imagine that's just some arbitrary function like I graphed here. And imagine we don't know a formula for it or couldn't find a formula for it, that this is just a stand-in. All right, well, the domain then are these points in the plane, right? And then the z-axis, that's where my values of the range come in. So instead of having a single value on an axis, I'll be approaching a point in the xy plane. So I'm going to identify this point as the point x naught, y naught. Right, that's the point I want to get closer and closer to, and then think about what the z's are doing. Okay, so the corresponding idea now. I'm taking a limit as a point in the domain, and xy gets closer and closer to a point x naught, y naught. My f of xy, I'm now thinking of as a z. For limits in Calc 1, I always tell my students that the limit statement is saying, hey, what do the y values do when x gets really, really close to something without getting there? For us, this limit statement is saying, hey, what are the z's doing when a point gets really, really close to this point in the domain? Okay, so now we can try to put all the things together, right? This limit should exist if I can keep my z values within a certain amount of a limit, right? And I'll call that L, by keeping the xy's close enough to x naught, y naught. So I could start off the same way. If for all epsilon bigger than 0, right? Epsilon is going to be a distance on my z-axis. So in fact, I could think about it being about that value on the z-axis, right? That's my L, and then epsilon would still just be some positive distance away, right? So I could go up from L and down from L, all in the range. If for all epsilon bigger than 0, there exists a corresponding number delta so that, all right, the z's, the f of x, y's, are within epsilon of L. This statement doesn't change whenever, right? I'm supposed to make that happen by keeping my points in the plane close enough to that point. Okay, well, what's that going to look like? When we're in the Calc 1 case, right, close enough means I just stayed in that little line segment, right, that was delta away on either side. That was the close enough part. What's that going to look like in the plane? Well, this little green interval I've shaded are just all the points that are less than or equal to, less than delta away from x naught, not counting the endpoints. So what I was really doing is identifying a spot in the domain where all the points were less than a certain distance away. And that's what I can do here. In the plane, I can identify all of the points that are less than a certain distance away. And so if I identified a delta that would work, and I'm not going to try to really draw what I think it is to match that epsilon, because drawing in 3D is hard. But if I just find all of the points that are delta away, right, if that point's delta away, I can imagine drawing the circle in the plane of radius delta. Instead of an interval in the domain to keep all of my points close enough to x naught, y naught, I have to be within that disk of radius delta. In fact, I have to be on the interior of that disk. Okay, well, I can write down a formula for that disk in the plane. If I'm just thinking about the circle, that would be x minus x naught all squared plus y minus y naught all squared. It would be equal to delta squared. Well, I want the points on the inside, so that's less than delta squared. And I don't want to actually get to the point itself. My function might not be defined there, so I'll just let this be bigger than 0 so that I'm always dealing with a disk of positive radius. And all of that seems very familiar, and instead of writing this down in terms of delta squared, if I just take a square root, everything is certainly still true. I'm only dealing with positive ideas of distance here. I'd end up with that statement. So I keep my z values within epsilon of L by keeping my x naught, y naughts within this disk of radius delta. So there's my definition of limit for these functions on more than one variable. One really neat thing about this is if I drop the y terms out, right, and imagine going back down a dimension, I have x minus x naught all squared, take a square root. Well, that would be x minus x naught in absolute value. This actually generalizes. The same way that in interval, all the points on a number line within a certain distance of the middle, well, a disk in the plane, an open disk in the plane is the same thing, just in that space. Those ideas generalize nicely. Okay, so that's the idea of limit, that if I wanted to keep my z values within epsilon of L, I have to keep my points in the plane in this region that would then map up and get me really close. That has to work for every positive distance, epsilon.